this tutorial, we're going to build a blob tracking effect in Max. So before we start, let's quickly go over what we're trying to achieve here. The main idea is that we will use the cv.jit package to track feature points within an input image, and then we'll draw windows over those points. So you can get this package in the package manager. So if you don't have it installed already, it will be under remote packages, but for me it's under installed packages. And when you click on launch, you can see all of the objects within the package. So strictly speaking, blob tracking would mean detecting connected regions in an image and then returning their boundaries. So this can be done using any of those objects, like the bounce object. But in this tutorial, we're going to use the cv.jit.features object instead, which is this here. So this tracks distinct points rather than full regions. And the visual result is very similar, but a bit easier to set up. So you can, of course, adapt this tutorial to also work with any of those blob objects here. Okay, so this tutorial consists of 4 parts. In the first one, we will set up the tracking using the cv.jit package. In the second one, we will use jit.gl.pix to draw just a single window. Then in the third one, we will move on to drawing multiple windows. And then in the fourth one, we will draw the frames around the windows. I will start with a jit world as the rendering context. Here I have a jit.p window. And this is an input video. Okay, then let's start with the first part, the tracking. So in order to do this first, I'm outputting a texture here. So let's first downsample it and then turn it into a matrix, because the CV package needs matrices to function. Okay, in order to downsample it, I will just create a texture with the dimensions 192, 108. So the input video is full HD, so 1920 by 1080. And so this is just the original dimension divided by 10. So that we can keep the aspect ratio. And then we'll say adapt 0. So this dimension won't change. Then we can use jit.gl async read. So this turns a texture into a matrix. Then in order for the cv.jit.feature object to work, we need a grayscale image. So now if we're taking a look at it, you can see that it's already downsampled, but it's still a color image. So in order to turn this grayscale, we can use the RGB to Luma object. So now it's a grayscale image. And then we can use the cv.jit.features object. So cv.jit, oh no, sorry, that's not what I meant to do. Features. So the output of this, so maybe let's use a jit cell block, take a look inside. So let's say plane -1. So what we're getting here are 2 planes. And each plane represents one axis. So the first plane represents the x-axis of the image, and the second plane represents the y-axis of the image. And then it will just, for each point that it detects, it will give us the coordinates in pixels. So in order to get the number of points, which we will later need in the jit.gl.pix, I will create another matrix this needs 2 planes, float 32. And then we can explicitly say adapt 1 because we want the dimensions to change according to the number of points we're getting here. And then we can use the get attribute object. So how can we do this? So every time a matrix comes through, at first I want to know the dimensions with this get attribute object, and then I will want to send it on. So we can connect the middle outlet to the inlet of the matrix. And then using a message here, oh, of course, we also have to specify what attribute we want to get, so dimension. So now we can see the changing dimension, and this dimension represents the number of tracked points we have here. Okay, and then because from now on we're going to work in jit.gl.pix, we can turn this into a texture, which we can then use in the jit.gl.pix codebox. So let's specify that this will be full HD again, so 1920 by 1080, and adapt 0. And let's put this to the side. Okay, so this concludes part 1. Now we can move on to part 2, where we're drawing a window. So I will just leave this here for now. We will need it later. Okay, so for part 2, first we need to set up our jit.gl.pix codebox. So for that, again, I need a texture, then jit.gl.pix codebox, and the rest of the code or the rest of the algorithm will be done basically in here. Okay, so we can connect the output to our JIT world. And then, so we also need this as an input in here. So maybe we can do something like trigger list. And then first, this was right. So first we're sending it here to do the detection, and then we'll send the full image to our jit.gl.pix. Okay. Okay, in order to draw a window, I will create a rectangle function. So let's maybe first set this first outlet to 1. And then we can say picture in equals in 1 for now. This seems to work. Then maybe also use a jit bang to bang this one constantly. Okay. So first I will create the function that draws our window. So let's call this one rect for rectangle, and the functions need to be declared on top of everything else. So what I want to give this rectangle at first is a scale. So this will determine the size of the rectangle, and a position. I will go over this a bit quicker. I did a more detailed description of this in my drawing shapes video, which I will put in the description. Okay, first we need our UV coordinates, which will be just the normalized coordinates. Then we will need half of the scale. I will show you in a minute why. So half scale, no, let's call this small h capital S. Half scale equals scale times 0.5. Then first we'll go, so maybe let's already set the output to our function so we can see what is happening. And then for the scale, let's say we're using 0.25 and the position can be just in the center. So 0.5, 0.5. Okay, so first we're going to create our x component. So x equals the position we specified here minus half of the scale. So imagine the position being 0.5, which is exactly in the center. So if I'm just saying position, then it would start at 0.5, but I want 0.5 to be at the center, so I have to subtract half of its scale. And then we're checking, is this smaller than our UV coordinates? And then we only need the x component of this. And let's just return x for now. Return x. Oh, sorry. So now we can see that everything that is smaller in x direction or in negative x direction will be black and the rest will be white. But we also need the other part. So then we can use the AND operator and essentially say the same thing. So I can copy this. But now I'm adding half of the scale and I'm checking if this one is bigger. So if it's bigger than the position plus half of the scale, it's also not part of our rectangle. And then we can again copy this whole thing for our y. And then just every time it says x, change this to y. And then, I mean, we can also return the y. And in order to get our rectangle, we can just say if both of those conditions are true, then we have our rectangle in the center at this size. So if we change the size, this happens. If we change the position, this happens. Okay, that's exactly what I wanted. Now I think we can move on to part 3, which is drawing multiple of those rectangles or multiple of those windows. In order to do this, first let's create a parameter for the number of windows. And then we can access this from the outside. So let's create a message, num windows. And this num windows parameter will be controlled by the number of feature points we're getting here. So I can delete this, plug this in here. And then while we're at it, we also need the position input. So let's call this one pos in. This will be input 2. So this is then this texture that we're getting here. So we can plug this in here. And also our number of windows. Let's maybe do it like that. making a bit more space here. Okay. Okay, so now we're getting the positions in here and we're getting the number of windows. But I think what I also want to do is, as a kind of a safety mechanism, I want to specify the maximum number of windows, because so essentially what we're going to do is we're going to create a for loop for each of those feature points, and we will draw this rectangle within the for loop. And in jit.gl.pix, this means that this for loop will be executed on every pixel for every frame. So if you would have something like 100 windows, this could be very demanding. So as a safety guard, to not kill our performance, let's create a parameter. Let's call this maxnum windows. And let's say, okay, for now, the maximum number of windows should be 16. And then I can already implement this. So what I can't do is I can't reassign this. So maybe let's call the input underscore num windows. Then also this one needs to be called underscore num windows. So makes it complain. Okay. So underscore num windows, and then we can create a new variable, call this one num windows, and set this to clip of the actual number of windows we're getting as an input. And then we're saying, okay, minimum is 0 and the maximum will be the maximum num windows. So this is kind of a safeguard, so we don't kill our performance. Then moving on to drawing multiple of those windows. So we have the positions, we have the picture input. So now we can create the for loop. So let's say for I equals, starting at 0, I is smaller than this number of windows we created here. I plus, no, sorry, plus equals 1. And now we need to find a way to access those points we got in here. So this takes the whole input image, and then we need to sample this image essentially exactly at those positions where the new points are stored. So as we're using normalized coordinates, we first need to know how big one of those bins is. So this is essentially, so bin size, bin size equals 1 divided by the number of windows we're having. Okay, I'm getting some errors because this is not doing anything at the moment. So let's just say for now x equals 1, so it doesn't complain anymore. Okay, back at it. So what I was trying to say is we will get, so we're getting, at this moment we're getting 8 positions. So the input texture is divided into 8 bins. And we're using normalized coordinates, so ranging from 0 to 1. So to get the size of one bin, it's just 1 divided by the number of windows we have here. And to create the position from which we will sample our input texture, we can just say sample position, and this is equal to I times the size of one bin. So at the beginning I is 0, and then we will have the first bin is at position 0. Then the next bin with 8 windows is at 1/8 of this texture, then at 2/8, 3, and so on and so on. But this will give us exactly the position at the beginning of the bin, which could lead to ambiguity. So I will also add a small offset, which is half of the bin size, so we'll get the position in the center of the bin, just to be safe. Okay, so this is the sample position. Then, okay. Then in order to get the position, we can now sample our position in texture at this sample position. So we only need the first two channels, and the way this matrix is converted into a texture, this will be alpha channel and the red channel. But now, as you saw earlier, so again with the cell block, these are pixel coordinates, and here we need coordinates that are normalized, so in a range of 0 to 1. So in order to get those in the right range, we have to divide it by the size of this input texture. So let's maybe create another variable, call this one posdim, and this is a vector. I mean, we could also use like this get attribute and then send it here, but I'm not going to change this, so we can just hard code it in here. Then we can say position divided equals this posdim, and then we should get numbers from in the range from 0 to 1. Now that we have our positions, we can draw a rectangle at this position. So first I will create a variable, call this one window size. Let's set this to 0.1 for now. And the thing is, now that we're, as I said in the beginning, we're not really doing blob tracking, because for blob tracking, you would get the bounds. So you would get left bound, right bound, upper and lower bound. And then you could use this to draw your rectangle. But as I'm just getting the position, I have to specify the size of the rectangle. So first of all, let's just draw a mask for our window. So this now is the rectangle function. So we're drawing a rectangle with this window size at this position we created here. And then let's just maybe set this to our output. So let's say mask equals 0. And then if we just do this, then this mask variable will be overwritten. So we have to do plus equals. So every new mask will be added on to the last one. And then we can just output the mask. And now we can see these moving windows. And if we compare this to our input, we can see that for all the birds, we get a window drawn here. What we can also do is we can, okay, this seems to be from before. So what we can change here is the distance and the threshold. So the distance is the distance in pixels, I think. So this checks if there are overlapping feature points. So each feature point has to have at least a distance of 5 pixels to the next one in order to be detected. So if we make this bigger, you can see that some of them are disappearing because they're too close. And if we're making this smaller, you can see that we have overlapping windows here. So let's just leave this at 5, but depending on what kind of input video you're using, it might be a good idea to just play around with those values. Okay, now we have the mask, and I think we can now come to the final part where we'll put everything together. So the idea now is that we will draw a frame around those regions. So this frame needs to be just slightly bigger than the mask. So For this, we can create a new variable, call this one frame size. And this, yeah, just set it to something small, 0.01. And then I'm also multiplying this by the aspect ratio of what's coming in. Because if I don't do this, the frame will have a different width for the X and the Y component. So maybe let's call this one frame width. And in order to take the aspect ratio into account, we can create a vector here, and we're dividing the Y dimension by the X dimension for the X component, and for the Y component, we can just leave it at 1. And while we're at it, we can also specify a color for our frame. So frame color, this will just be a vector free. Let's say, yeah, make this one red for now. Okay. So in order to create a frame, we essentially also need this rectangle. So frame equals this rectangle again, but in this case, we don't just want the window size, we want the window size and this little frame width offset, so it's bigger. So the idea is that the mask will just show the picture, and then the frame is this little offset around the picture, which we will then color in red. And then the actual window will be, so wait, I can get rid of this mask here. This will just be declared once. And then the window itself will check, okay, either we're drawing the frame color or we will draw just the picture that's coming in. And this will be decided by the mask. And then to take a look at what that looks like, we can just set window to 0 here, then window plus equals this, and then we can output it. So now you can see that we're either drawing the picture that's coming in or we're drawing the frame color. And then to create the final image, let's call this one. So let's declare this one up here again. So picture out is 0. And then we can say picture out equals. So now we're using the mix operator again, because we're now saying, okay, either take the picture out we already have, or use the window we drew here, and this will be decided by the frame itself. Because the frame is a bit bigger than the window, everything that will be left will be exactly a frame around this one. And now you can see that we're drawing these moving frames. And as you can see, now that we're using this mix operator, even if they're overlapping, they won't be drawn on top of each other, but it will be either one window or the other window. But yeah, I will put this picture out here and just set it to our input picture, because then we'll have the frames drawn on top of just a normal input picture. Okay, so this was essentially part 4. I mean, a small bonus thing we could do would be, so you could always change the picture that's within those frames. So if I'm doing something like 1 minus this picture in, then the pictures within the frames will be inverted. But what I also like to do is zoom into those regions, which can be quite fun. So in order to do that, we need a zoom UV. And again, I will just do this very quickly. If you want a more detailed description of zooming and rotating textures, I also made a jit.gl.pix intro video about that, which I will put into the description. Okay, so the zoom UV will be our normalized coordinates minus our position. And then we divide this by the zoom factor. Let's just say this is 4. And we also have to add the position as an offset in here. And then instead of just taking the picture in as it is, we need to sample it with our zoom UV. So pick in and then sampling this with the zoom UVs we created here. And now you can see we're zooming in. We can also make this even more extreme or just a slight zoom. What we could also do is, instead of, if you want to do the processing outside of this jit.gl.pix, you could create a third input and then do some processing on the outside, and then use the third input in here in order to show the contents of the windows. Okay, but I think that's it for this tutorial. That's all I wanted to show you. I hope you found this useful, and thank you for watching.